still the disturbance is there.
But it has improved.
Let me just see, switch to another. Is it better now?
Yes, we can hear now.
Me, is it better?
Yes.
Yeah, great. Okay, so what I'm saying is that so if you have to, for example, predict whether the machine is going to fail or not, I need to have sufficient past data of these attributes of the machine, like temperature, pressure, vibration, whatever, which are likely to lead to a failure, as well as I have to have the data that against a particular instance of time, when all of this data has been captured, whether the machine failed in the past or not. Okay. So unless I have that data ready, I'll not be able to build a what is called a supervised machine learning model. Okay. So many times the organizations take a lot of years to actually get ready with the data before they can even work on these things. Okay. So when we discuss about the data that you can actually get, at that time, probably you will be able to figure out whether this type of data is available in the organization in the first place or not. Okay. If it is not available in the organization, obviously you can't do anything with that. Then the first step would be to get that data before you can do anything. Okay, on that. Okay. Does it make sense?
Yes.
Yes.
Yeah.
Okay. So we will probably get back to this. I think then it will make sense when once we have understood the various types of machine learning problems. Okay. So I'll open our presentation. Just give me a second. Okay, I think we have discussed this that the data-based decision making versus physics-based decision making. Did I talk about this very briefly in the first section? How machines learn versus the formula V equal to U plus FT? Yes, no? Anybody remembering?
This photo.
No.
No, this
slide
picture
we
I
have
did
not
not show, but this picture I did not show. But I talked about.
But you
I think
did mention about the simple data with the formulas and also the big data.
You
No,
just
that
spoke
is
about,
different.
whether
What
it's
that
you can do prediction or not with the
no,
formula that we spoke.
yes. So I was talking about physics based. So if you have V equal to U plus FT, that's a physics based prediction. Okay. Whereas when I am trying to use machine learning is database prediction. Okay. And these are two very different things because in physics-based prediction, you have a formula V equal to U plus FT or whatever. Okay. Based on that, you are predicting V. But in database prediction, you don't have a formula. Why you don't have a formula? Because the formula is too complex. There are too many variables. So you just know that something is dependent on something. Like we write, right? Y equal to fx. So this equation means that we know that y is dependent on x, but we don't know how y is dependent on x. Sometimes for example, if you write y equal to mx plus c, if I know m value, c value, and x is only the power is 1, I know how y is dependent on x. But sometimes I do not know how y is dependent. I know y is dependent on x, but I don't know how y is dependent on x. A very classical example is, let's say, salary versus years of experience. I cannot make a formula, right? I know that if the years of experience increases, the salary in general will increase. I know that much. But there's no formula. Now, interestingly, there are certain type of jobs, let's say like government jobs and all, and sometimes even large organizations, they convert that to a formula with saying that if you have so many years of experience, every year you will get an increment like this, etc., etc. But in most organizations, it's not like that. There is a dependence, but there are many other factors. There are factors of performance, there are so many other factors. Okay, the skills. So I know that there is a dependence of salary on years of experience, but I don't know how. I know y equal to fx, but I don't know what is the formula. Now here, if I have to predict salary given the years of experience, how do we do it? This is different from what we are saying physics-based equation, where we know the formula, and once the formula is known, it is a no-brainer. Okay. But where you don't have the formula, how do you do it? So the only way I can do it is collect past data, or rather, in this case, it may not be past data. It can be data of many other people with the information of years of experience and the information of salary, and find out the best possible relationship between the two. Remember, I am not trying to necessarily find out the most accurate relationship, because I cannot find out the most accurate relationship. I can at best find out the best possible relationship. And looking at the data, probably I'll be able to say that the best possible relationship is something if I draw a line like this. Right? Now, once I'm able to draw the line like this, if I know somebody's years of experience is this, I can approximately predict that the salary will be this much. This will never be accurate or 100% accurate, but I would be able to say with reasonable degree of accuracy that the salary will be this much. Now, my attempt in any machine learning problem is essentially to arrive at this kind of approximation. Okay. Obviously, the question is, what is the best approximation? Because here, by eye estimation, I drew this line. But I need to get to a mathematical formula based on which I can find out the best possible approximation. So what is the mathematical formula doing? The mathematical formula is not trying to find out the exact relationship between year salary and years of experience, but trying to find out the best possible relationship between salary and years of experience based on a large number of data points that I have collected. This concept is called data-based decision making. And interestingly, it is found that actually human brain works more on data-based decision making than physics-based decision making. The way we think on database. That's why when that's why Messi can hit a goal with a perfect parabolic motion without even knowing an iota of, presumably, what does parabolic motion mean? Or Virat Kohli is hitting the perfect six without knowing, where what is the exact angle of the bat in which you should hit the ball. Okay, So human brain works on database decision making, not physics-based decision making. Physics-based decision making is always slow. Database decision making is fast, but it requires a lot of data. So in case of Virat Kohli, in case of Messi, the data is the number of times they have practiced. Okay. So far, everybody clear? Makes sense?
Yeah.
Now, what is this fundamental method by which we find out that this approximation is the ideal approximation? That concept is called gradient descent. Okay. What is this gradient descent? Gradient descent means that in this method, there will always be an error. There will always be an error between the actual value. Let's say the actual value here was this. The actual salary is this. And the prediction is this. There will always be an error. Okay. The way to find the best solution here is to start at any random point. Random point means let's assume that this is the line that defines the relationship between salary and experience. Start with any random line and then start iterating. That means once you get this line, there will be an error. Error in terms of what the actual salary is and what it is predicting. So as per this blue line, the prediction is this much and the actual salary is this much. So this is the error. Okay. So for every point, there will be an error. And we can calculate the error because this is based on past data. We already know what was the actual salary and we are trying to predict the salary based on this line. So it is possible for us to find out the error. Now, what is our objective? Our objective is to ensure that this error is minimal. Now, how do I make the get to the point of the error is minimum? I try to move this line. There are two ways I can move this line, either this way or this way. Either downwards or upwards. Now, if I move upwards, let's say I move some delta upwards, then I figure out what is the error. And I see if the error is higher than what it was before. If the error is higher, then obviously this is not the right direction to move the line. On the other hand, if I move the other direction, I see that the error is lower. So this is the right direction to move. So I'll move the line like this. I'll not stop there. I will further move this. So I know the direction in which I should move to get the lowest error. And I should go on moving this line till I reach this black line, which is the ideal line, because if I move the black line further, then the error again increases. I'm getting a minimal error. And where I get the minimal error, that is the most optimal line. So this concept is called gradient descent. Now, why it is called gradient descent is because you are descending down the gradient of error. So think of it that you are sitting on a mountain and you want to reach the base. So the error is the point at which you are sitting versus the point of the base. And you need to figure out how you should move down so that the distance between the base and you is minimal. Interestingly, when you see later, you never want to make this error 0. Okay. You never want to make this error 0. You always leave a certain amount of error. Yes, you really don't need want to reach the base. You probably want to reach somewhere here. Now, why do you do that? We'll see that later. But the whole concept is that you keep measuring it, and so there can be, let's say, if you are sitting somewhere here, you know that if you move up, your error is increasing. If you move down, your error is reducing. There can be other problems. For example, the mountain can look like this. So here, if you reach, okay, you see the error is at a certain point, then you move up, okay, and you see the error is going down. But that doesn't mean that moving this up is actually the right direction compared to moving this way up. Because if you go this way up, then you can again come down. So there are some concepts of local minimum and local maximum. And those are little advanced concepts, but basically what we're trying to do is we are trying to minimize the error between the actual value and what the model has predicted. Okay? And this entire concept is called gradient descent. Now you may say, what's the big deal? I mean, it's a very simple equation. You can always find out the distance between this point and this point. Anybody can do that. What's the big deal? Of course, there's no big deal. And this is not a big deal at all, because all these theories are not new. New theories or latest theories. Okay. What was the big deal? The big deal was the iteration, the number of times you have to do to finally arrive at this black line. And that was restricting processing this kind of huge data. So what actually has happened is, because of the increase in the computational power in last couple of decades, the machine learning or data science has picked up simply because that it has helped in computing huge amount of data. So these iterations you could have probably done only 4 or 5 times manually. But now I can do it thousands and millions of times to get the best results, to do it to the large amount of data sets. Okay. And because remember, it's not just one parameter on which I am trying to do it. I can do it against multiple parameters. For example, it's not just salary versus years of experience. It is salary versus years of experience, education. So there can be multiple parameters. Okay. So far, fine.
Yes.
Yes.
Great. So this is the broad thing that we are trying to do. And within this, there are 4 major techniques. The classical machine learning, there are 4 major techniques. I am not talking about deep learning. So you have machine learning, then you have deep learning, and today we have generative AI and agentic AI. That's the circle. Okay. So you have machine learning, you have deep learning, then you have Gen AI, and then you have agentic AI. So this is the circle. So we are talking about here machine learning, okay, which is again a part of overall AI. So there are 4 major techniques in machine learning. One is called, the first one is called regression. What is regression? Regression means that I'm trying to predict an outcome which is of continuous nature. For example, salary. Salary is a value that can have any value. Okay. And I may say that I can predict salary based on years of experience. I may also say that I want to predict salary because I know there are multiple parameters on which salary depends. I know that depends on years of experience. I know it depends on education. It probably depends on the industry. It depends on your past year's performance. So I can easily define 4 or 5 parameters on which salary depends. But I remember I don't know the formula. I don't know the formula. If I knew the formula, then it will become physics-based model. I don't know the formula. I know it depends on industry, but I don't know what is the formula. So I want to predict salary based on these 4 or 5 parameters. Okay. Because salary is a continuous value. Okay, I'm not predicting whether salary is high or low. I'm predicting the salary is 5 lakhs or the salary is 20 lakhs. So I'm predicting a certain value. That type of problem is called a regression problem. Okay. Is it clear, everybody? What is the basic meaning of regression problem?
Yeah.
Yes, no. Okay. Now, within regression, there are various types of regression. For example, here we say that salary and years of experience, we assume two things. First of all, we assume that salary is dependent on or dependent on years of experience, or we have only the data about years of experience. We know that it may depend on other things, but we don't have the other data. We just have the data about years of experience. And even though we know that it may depend on industry, it may depend on education, we don't have the data, or we have not collected the data, or we think the data is not that important. And we are predicting salary based on only years of experience. That's the first assumption. The second assumption is that we think, kind of eyeballing the data, that the best fit is a line, is not a curve, is not something like this. It's not something like this. That's an assumption that we have made. Okay, in the beginning, when I said that is a line, I made an assumption that the best line or best equation to predict the salary and years of experience will be a linear equation, will not be a polynomial equation. So I made two assumptions. First assumption is salary depends on what years of experience only, or at least that's the only information that we have on which we are basing the salary prediction. The second is that it is a linear relationship. Y equal to fx is a linear relationship. It's not a polynomial relationship. This type of equation is called a simple linear regression. Simple because it depends only on one variable. Linear because it is one degree equation. Okay, so far fine. However, if I thought that no, it may not be a line, it may actually be a curve. Okay. Then we are talking about simple polynomial regression. Simple polynomial regression. Now, how do I know that whether it should be a line or a curve? That will depend on few factors. We'll talk about that. Okay. Now let us look at the other aspect. The other aspect is that here we have assumed that the salary depends on only years of experience. At least it may depend on the other factors, but that's the only factor we are considering for building our model. So this is a simple regression because it depends on one factor. Suppose we say that no, it depends on other factors, and we have the data for that, like industry, like your skills, etc. Then it will no longer be simple. It will be so the simple linear regression, and then this is multiple linear regression. So because it depends on multiple factors, not on one factor. So regression consists of simple linear regression, simple polynomial regression, multiple linear regression, multiple polynomial regression. Okay, so far fine, everybody. The concept.
Yes, Professor.
Now, obviously, another question might come to your mind, that who determines what are the factors on which salary will depend? I think of it. Let's say you are embarking on a machine learning project where you want to predict the downtime of a machine. So predicting the downtime of a machine is a different type of a problem. It's the classification problem, because there you're saying that whether the machine will be down or not down. But let's assume mean time between fail. You are trying to predict mean time between failure. So that's the number, right? It is not yes or no. That's a number. So that means it's a regression problem. Okay. Now you know that this mean time between failure depends on multiple factors, like maybe the age of the machine. So there are certain factors which are you can say which are characteristics of the machine, general characteristics of the machine, like age of the machine, whether the insurance has been done or not, whether what was the last time the machine was serviced. So these are certain factors, and there are certain factors which are based on the real-time performance of the machine. What is the temperature of the machine at this point of time? What is the vibration of the machine at this point of time? Okay, so those are real time. Like age of the machine, whether insurance is available or not, is something like it's more like a batch data that is available. You have to consider both to find out the mean time between failure. Now, who do you think will determine this? What are the factors? Who do you think determines this? Will it be a data scientist?
The maintenance
Yes, no.
team.
So obviously, it has to be a maintenance engineer. So many people feel, see, this is where when you try to set up a data science project, what is the starting point? Many people think that the starting point is the data science team. No, the starting point is the business. Because the first thing that what are the factors on which a particular outcome will depend, whether we talk about machines or we talk about, let's say, customer churn, whether a customer will stay with me or customer will leave me. Or let's say, what will be the customer lifetime value? What are the factors on which the customer lifetime value depends on? The sales and the marketing team has to provide that. So always the starting point of a data science project is the business. It is never the data science team or the IT team. They can't do anything unless you first of all say, this is my use case. This is where I want to use data science. I want to use a machine learning model. You have to say, if you are from the maintenance department, you have to say that I feel that predicting the failure of a machine is a good use case for machine learning. It is unfair to expect the IT team to come and tell you that why don't you use machine learning for your predicting your failure of machine, because they don't know your business. You know your business, so you have to say that yes, this is a good use case. Second, after I say I have to identify what kind of machine learning models I require. That's where regression, classification, etc. will come in. So I have to identify that. Then I have to say that these are the parameters on which my output will depend. All this, remember, nothing is being done by the IT team. This is done by the business. Then you have to say, okay, these are the factors which, based on my experience of the domain, I need to get the data. Do I have the data for that? That collecting the data itself may 3-4 years if you are absolutely starting from scratch. Because if you don't have those data, you have to find out from where you get the data, you have to see where you store the data, etc. Okay, and of course, the IT team can help you to do that, to get that data. Okay, how to bring that data. Only when I have got sufficient data, then only I can start doing anything on machine learning. Okay, so that's why it's very, very important that the initiation happens from the business, does not happen from the IT. Okay, so this is regression and the different categories of regression. Of course, we are going to talk in greater details when for each of these things. Okay. Time series. Time series is also prediction. Classical example of time series is stock market, right? So you predict what will be the index tomorrow. But The difference is that in case of regression, the input parameters, which we call also as features, the input parameter on which you are predicting is also called feature, and the output is called the label. So this is a feature, years of experience a feature, and salary is a label or an outcome. Okay. So so the features in case of regression is not time. Is years of experience, is skill, education, etc., but not time. You are not predicting salary based on my salary of last 10 years, which is the case because of stock market. In stock market, you're predicting the stock market mostly. There are other methods of prediction. Mostly you're predicting the stock market based on how the stock market has behaved in the past. That type of prediction is called a time series prediction. Time series prediction assumes that all the features that affect the outcome has been absorbed in time. That means stock market may be affected by the general economy, may be affected by performance of the company, etc., etc. Okay, but all of them, I'm not considering any of them as features. I'm assuming that all of them have already been absorbed if I look at time. See, the time series data has already considered that if the economy did well in the past, the stock market would have gone up, etc. As a result, one of the biggest drawbacks of this time series analysis is they cannot, or they are not very good at predicting what is called a black swan event. Black swan event means an event that happens, has not happened in the past, or probably has happened very long back in the past. Something like a pandemic. So a time series cannot predict that the stock market will go down for a pandemic because it cannot predict there's a pandemic. Because that data, information about the pandemic has not got absorbed in the time series because the pandemic has never occurred in the past, or at least in the recent past. Similarly, a war. So today, for example, for stock market analysis, you not only look at time series, you also look at various other regression parameters. For example, whether what are the sentiments floating around in the Twitter. So those are better in predicting the black swan event. For example, let's say in the early days of COVID, probably there will be sentiments floating around in the Twitter or X that there are so much of disturbance happening because of this likely or impending pandemic, okay, or about a war, okay. So those things can be found out from other means than time series. So these days, when we try to predict stock market, we are not only predicting based on time series, okay, but time series basically means that you are predicting based on past historical data, and even in many cases, time series works very well, especially for stable businesses and all. Even many of the sales forecasting and all of many large corporations are also as done on time series because it's considered good enough for the purpose. Okay, so far fine, everybody.
Yes.
Great.
Yes.
Now the third category is called classification. In classification, I am not, the outcome is not a continuous value. Outcome is not a salary. Outcome is not mean time between failure. Outcome is whether the machine will fail or not, yes or no. Whether the customer will leave or not, will churn or not, yes or no. whether a patient is diabetic or not. Okay. So essentially, you are trying to classify in certain buckets. That is the classification problem. Now, in general, how does classification problem works? Classification problem actually is nothing but a modified regression problem. Why do I say so? Because in a regression problem, we are giving an output which is continuous. In classification problem, also the output is a continuous value, except the fact that this continuous value is the probability. So when I say machine will go down or not, will break down or not, we are not actually predicting yes or no. We are predicting the probability of machine breaking down. And then once we have a probability, 0.1, we all know probability is 0 to 1, 0.1, 0.2, 0.7, 0.8, we are applying a cutoff. So let's say any probability above 0.5, it will indicate the machine will break down. And any probability below 0.5 will indicate the machine will not break down. So we are forcefully applying a cutoff, and then we are saying that above the cutoff, it is one class, and that's why it's called classification. One class, which is the machine will fail, and if it's below 0.5, the other class will mean the machine will not fail. Okay. So in a way, a classification problem is also a regression problem. It's a modified regression problem. So far, fine, everybody?
Yes.
Now, these three techniques in classical machine learning, they are called supervised learning. There in the previous, supervised learning. Now, why it is called supervised learning? Because as we saw in the previous the salary example, that I need to provide the data to the computer or the model, and the data must consist of both the input parameters and the output parameters. I have to give the data of years of experience, and I have to give the data of salary. I have to give the data of the various medical parameters, and also have to give the data that whether the patient was diabetic or non-diabetic. So I have to first give that data. And then I have to ask the machine to conduct various trials and errors, like this drawing this black line, conduct multiple trials and errors in such a way that the error is minimal. Now, how do we define that error? That will depend on the type of model that we're talking about. For example, in case of a model like regression, the error is defined in terms of the difference between the actual salary and what the salary this particular line predicts. But in case of classification, that will not work, because in case of classification, he was saying that whether somebody is diabetic or non-diabetic, whether the machine will fail or not fail. So there is no continuous value that you can measure. So there you have to measure something else. There you have to measure incorrect classifications. For example, how many times the model classified that the machine will fail, but actually the machine did not fail. Why can I say, how can I say actually the machine did not fail? Because I already have the data, whether the machine actually failed or not. And I'm asking the machine that you predict based on whatever parameters you have given, and then I'm going to check whether your prediction is correct or not. Okay. So essentially, I'm trying to figure out to what extent the error has been minimized by finding out the misclassifications. So the parameter on which I'm going to measure the error will be different based on the type of problem that I'm machine learning problem that I'm trying to solve. Okay. Now, because these have to be based on past data where both the input and the outcome are defined, hence they are called supervised machine learning. Okay. Also because this has to be, the error has to be measured. There has to be a process by which the error can be measured. And this is called the training, testing, validation set. Training, testing, and validation. What do I do in training, testing, and validation? I first have a data set which has all the input as well as the outcome. I have to give this data set to the model to train itself. That means to find out the best fitting line or find out the best logic. And then I have to give a data, another data where I know the outcome, but I don't tell the outcome to the model. Okay. I just give the input parameters. I have the outcome, but I don't give it to the model. I now tell that now that you have developed a model, you have found out the solution, predict the outcome for me. And then I'm going to check that it's like an examination. So one is the class, the training is the class that I'm giving the data to the model to train itself, and test is the examination I'm taking. And obviously, now a very interesting question will come, which is that my examination can be of two types. One examination is that you have you have last 10 years question paper available, and your examination is coming similar to those last 10 years question. Okay. Another examination is that the pattern becomes very different. Many times, when children appear for examinations, we find that this year's the pattern was totally different. It was within syllabus, but the pattern was very different. It is not following last 10 years pattern. Okay, so the question is that how do you like to test? Now, interestingly, two different types of students will perform better in two different types of tests. So, for example, let's say a student, there are two students, A and B. Okay. Student number A, he has studied very seriously all last 10 years question papers. Okay. Absolutely solved all sets of question papers. Okay. But not very strong in fundamentals. Didn't go into basic fundamentals, but solved all the question papers. And student number B, she has focused only on fundamentals. She didn't look at last few years question papers. Okay. Now, question to you is that suppose there is a question, scenario one, the question paper that comes this year is very similar to last 10 years question paper. That means probably if I studied the last 10 years question paper, I've actually got common questions, what we typically call common questions. That means same question repeated maybe 3 years back, 5 years back, same question has come. If the question paper is like this, which of these two students will perform better, student A or student B? What do you think?
We have to
Student
go
A.
to the time series analysis over here.
No. Okay, this is just an analogy. Don't worry about the regression or time series classification. Just an analogy which is relevant for any kind of supervised learning. So regression, time series classification, all three are supervised learning. Because I am giving some study materials. It's a class and then the exam. Like this one. You are attending some sessions, and based on these sessions, there will be an exam. This is supervised learning. As opposed to if I just say that go and do whatever you like, study from YouTube, whatever, I'm going to conduct an examination. That is unsupervised. So this is supervised learning, what you are doing now. Similarly, regression, time series classification, all is supervised learning. The analogy that I'm drawing is for supervised learning. In the first scenario, I am saying that you have, and I'll draw the parallel between the analogy. Okay, you have a scenario where you have studied all the student A has studied all the question papers for last 10 years, solved all the question papers, and then the question comes which is very similar to last 10 years question paper. And another student who has not solved, not even seen last 10 years question paper, but her fundamentals are very clear. Concepts are very clear, but she has not gone through the question papers. Somehow she didn't have access to the question paper, whatever. If that examination comes where the questions are very similar to the last 10 years question paper, it has followed a pattern, which of these students, student A or student B, will perform better?
Student A.
Student A will perform better. Okay. So that's what the coaching institutes do today. Okay. So, all the difficult entrance examinations that the coaching institutes will prepare you for last few years question papers. And if the question papers come exactly the same pattern, you are likely to do well. If the pattern breaks, if the question paper comes which is different from last 10 years question papers, nothing is common. It is within syllabus. No common questions. It is based on certain fundamentals. Which student will do better?
Student B.
Student B will do better. Which student we want? Let's say you are about to recruit one of these students in your company. You want student A
B.
type employees or student B type employees?
Student B.
Student B type employees. Why?
Because knowing the fundamentals is more important than scoring the marks in
Why?
reality.
Why?
Because if the concepts are not clear, they will
Scoring
not be
the
able
marks.
to apply.
Okay, scoring the marks. Okay, don't get so student B will score better marks in the second category of exams, where it is not following the pattern. Okay.
Yeah, but knowing fundamentals is important. Otherwise, they will not be able to apply those concepts what they have learned in the real work. So in the end, what matters is how much understanding they have and how they apply that understanding. And therefore, it is student B who is preferred.
Yes, the reason is that things that are happening in real life may not follow a pattern.
Yeah.
That is the whole idea. It may not follow an exact pattern. Okay, so similarly, when you build a machine learning model, there is a trade-off. Do I want to build a model which will predict very accurately if the future data follows exactly the same pattern as the past data? Or do I want a model where even if there is significant variation of the future data compared to the past data, still the model will be able to predict reasonably accurately. In many occasions, there is a trade-off. You actually cannot also go only for the second one, because if it is the second one, when there is a very regular pattern, data in pattern, then the model will do very badly, because student B does very badly when the question pattern is the same. And student A does very badly when there is a deviation from the pattern. We need a mix of both. That is the ideal scenario. We need a mix of both. Okay. Similarly, models also we need a mix of both. A model that can perform reasonably well if the data pattern is similar to the past data, and the same model should be able to perform reasonably well when the data pattern is very different from the past data. This particular trade-off, we'll talk about this in greater details, don't worry. Okay. This is called the bias variance trade-off. Bias variance trade-off. The very, very important concept in statistics. Okay. But we'll talk about this in greater details. I'm just giving you the broad ideas. Okay. So we talked about 3 supervised learnings methods: regression, time series, classification. We also talked about the different types of regression: simple, multiple, and linear, polynomial. And of course, the fact that classification is nothing but a variation of regression, because in classification also we predict the probability, we don't really predict the class. And then we talked about this bias variance trade-off in through an analogy. Now, clustering is another type of a machine learning problem. Some call it descriptive analytics also. Why? Because clustering is not supervised learning. Clustering is unsupervised learning. Now, what would be an example of clustering? Now, many of you know, especially from perspective of children's education, even in this, when you're doing this course, how is your marks, or rather, how is your results declared? Is it in terms of marks or is it in terms of grade?
Both. Marks and grade.
Tell me, what is the need for grade? Okay,
No,
so
finally, the
you
mark
are
sheet
given
has only
marks that the
grades.
student. Yeah,
That's
so
what is
student
imaging.
student A has got 74.5, student B has got 74, student C, or let me say XYZ. Okay. Just kidding. So student A has, X. Student X has got 74.5. Student Y has got 74. Student Z has got 30. Student A has got A. X has got A, and C. Now, why do I need grades? Why fill one extra column called grades? The marks, wouldn't that be sufficient? In fact, previously, grades is a very recent phenomenon in the education system. If you talk to your parents or even grandparents, they never knew what was grades, right? They just knew marks. 60% and higher is first division. That's what they knew. Why do we have grades in this
It's a
education
relative
system?
relative
Relative, I
differences.
can find out. Marks itself is, there cannot be any better relative than marks. Here I can easily find out X has scored 74.5 and Y has scored 74. So X is better than Y. In fact, with
It's
grades,
like
I cannot differentiate.
it's like you are making a group of some range.
Why do I need to make a group? Why should I make a group? X has got 0.5 marks more than Y. Why should I, make put X and Y in the same group? Basic question, right? These days, even the
We also had the same doubt.
sorry.
We also had the same doubt why grading is required.
Very, very important question. And you'll also see that why, the entire concept of grading, the purpose for which grading was there done, and the way it gets implemented, the entire purpose gets defeated. So nothing to do with machine learning per se, but it's very interesting to know that. That's why we always should know what is the first principle, why something exists, the reason which it came. Why did grade come in the first place? Okay. So what is the principle behind grading? The principle behind grading is that there is no difference between X and Y. Okay. You might have studied this concept of hypothesis, null hypothesis, alternate hypothesis. Did you with your statistics?
Yes.
Okay. So if I convert this in the form of a statistical hypothesis, the hypothesis is that there is no null hypothesis, there is no difference between student X and Y. Okay. Alternate hypothesis is there is a difference. And when can I reject the null hypothesis? I can reject the null hypothesis when the p-value is less than 0.05, right? 5%. And what is p-value less than 0.05 mean? P-value less than 0.05 means that there is a significant difference in the value between X and Y. So to answer in a very simple language, what statisticians are saying that 74.5 and 74 does this indicate a real difference, or this difference was due to chance? That X scored 0.5 marks, was it because of an assignable cause that X was better than Y, or it is just a chance? It's just, next I take another exam, Y makes 4.5 more than X. It is just chance because of which X has got this 0.5 marks. Grading is expected to negate this element of chance. So I am putting X and Y in the same grade because I believe there is no true difference between X and Y. The difference in marks is only due to chance. But I do believe there is a big difference between X, Y, and Z. This difference in marks cannot be due to chance. Z is definitely a weaker student than X and Y. And when can I say that the difference is big enough to say that Z is different from X and Y? That is when we use this null hypothesis and say that if the p-value is less than 0.05, then we say that this difference cannot be due to chance. This must be different, really different. That is the whole purpose of grading, to eliminate any vitiation of the outcome due to chance. Is this clear so far?
Yes.
Now, can you tell me, nothing to do directly with clustering, but in general, that helps us to identify where we should apply clustering. So basically, this is clustering. So grading is a very basic example of clustering. We are doing clusters based on marks, and we are doing clusters in such a way that the objective is that we do not want to differentiate students whose difference in marks is likely to be due to chance rather than a real difference between the capability of the students. Okay. Taking the same education example, can you tell me some use cases where this grading system is wrongly used, incorrectly used? And actually, you should use mark system, not a grading system. Any example?
Health, blood samples,
No. In education only.
education.
Competitive exams. Competitive
Examinations. Absolutely right. So how does competitive examinations work? Competitive examinations assumes that there is a fixed number of seats or availability. Moment you have a fixed availability, let's say an institute can take 100 students, okay, or why just educate, even if you look at recruitment, moment it is fixed that you can recruit, your recruitment plan says 100 recruitment, 100 fresher recruitment this year. That's fixed. It cannot be 101. What is the problem there? Problem is that X with 74.5 gets in because he or she is within the 100, and Y with 74 does not get in because he or she is outside the 101st. And your dictat says that you cannot have more than 100 employees this year. So you are defeating the entire concept of clustering. So either you say that, yes, there's no way I can have more than 100 employees. So I have to accommodate for this variation due to chance. I have no way to eliminate that. Y is too unfortunate to go out. Or you have to say that my recruitment, my entrance has to be within a band. It cannot be exact 100. It has to be 100 to 150. So that it is up to my discretion that I take the 101st candidate who has also gotten A. Now, unfortunately, most of our systems, whether we talk about education or we talk about recruitment, does not understand this fundamental concept, because of which they don't give a band. See, if they give a band, if the IIT seat says that, okay, your seat in this IIT can be between 700 to 800, then this problem gets solved. Or let's say when a company is recruiting, when TCS is recruiting, TCS says that this year my recruitment can be between 1,000 to 1,200. Then this problem gets solved. But that's not how we work. And that's a big problem. So we defeat the entire concept of grading. Even in your case also, you might be seeing that in many institutes do that. I'm not sure whether BITS Learning does it. That there is a kind of you can say a cap, that the maximum number of students getting A cannot be more than 30%, or the number of students getting A cannot be more than 30%. Moment 31 students get in out of 100, the management will say that no, this guy cannot get an A because the maximum is 30. And the poor guy has got 74 instead of 74.5, so the cutoff is 0.5. So even with a very small cutoff, you lose a grade. The whole purpose of grading is lost. That is not the spirit of grading, right? But again, why such institutes do this? Because some people manipulate this. Some will give everybody A grade. Some will give 50% of the class will get D grade. Okay, different faculty have different type of idiosyncrasies, right? So somebody will be very lenient, give everybody A. Some will be very strict. Okay, give 50% D. And because of this, some institutes kind of impose this, but that defeats the entire grading process. Okay, so I'm sure there are better ways of handling this kind of thing, but it should not be this way. Okay, so far fine, everybody?
Yes.
Okay, great.
Yes.
So obviously the question may come that what is the practical use of other uses of clustering in real scenario? A very classic use of clustering is, let's say, customer segmentation. In marketing, you might have studied segmentation, right? So segmentation is basically different attributes of a customer that are common for the series of customers, and you create segment out of that. Now these days, you have so many different attributes that can be collected by data. Through different data. So previously you had only limited attributes, for example, age, gender, etc. Now you have more than, let's say, 10,000 attributes of a customer. What are they doing in their website? What are they doing in their app? Which pages they went? Which page they spent how much time? Whether they downloaded a brochure? All of these things. Whenever you go to Amazon, whenever you go to any other website, all this data, your entire behavior in the website is captured. And based on that behavior, it is possible to group together customers in terms of certain attributes. For example, certain customers may be they are explorers. That means they spend a lot of time on the website, but they don't buy anything. Another set of customers can be very fast buyers. They just go and buy. Okay? All these type of attributes can be grouped together, and the behavior of these customers can be studied. So the entire concept is called clustering. Clustering, unlike the first three, is not a supervised machine learning technique because it doesn't require training data. I'm not giving a separate data and saying that to group them together. I'm giving, this is the marks of the students, group them in 5 different subjects, group them together. There's nothing training, there's no training data here. Okay, so far fine, everybody. So we will be mostly in this course talking about these 4 different methods of uh, prediction. Okay, we talked about supervised, unsupervised. Let us now talk about this.
Professor, why
Yes.
it is called as unsupervised?
Yes, unsupervised, because in case of supervised, what you're doing, you are supervising the model, the way the model is going to learn, but by providing an already a data set that has all the information. It has the information about the salary as well as the employee's age. So
It has a historical data.
It has the historical data of both the input and the output, not just the input. Correct.
And in clustering, we have only the input and we don't have the historical output data.
Yes, because I don't know, there is nothing called a historical data of the grade of the student. The grade of the students is based on the current marks, right?
Okay.
So there is nothing to get trained on. Okay. So far fine, but any other question? Okay. So let us look at regression as the first kind of basic model. In fact, some people say regression even came before machine learning. This was the basic statistics techniques use regression. So some people even say that this is not really a machine learning. It was a basic statistical method that was available earlier on. So here you see that the first example that is said that linear regression versus polynomial. So in linear regression, you have this y equal to beta naught plus beta 1 x. Okay. So this is a simple linear regression. Okay. What will be multiple linear regression or complex linear regression? Can anybody tell me, just so that what will be the equivalent of multiple or complex linear regression? What will be the equation for that?
Beta 1x plus, it's not polynomial you're asking, no? It's multiple
No, not
linear
polynomial.
regression.
Yes.
Beta 1 and beta
1 what?
xy.
X Y, no. Can be XY.
X1, X2 like that.
X1, right. Beta 1, X1, beta 2, X2 to beta N,
All right.
XN. So X1, X2, X3 are the different input variables or features. So in a simple linear model, X is salary, and in multiple linear model or complex linear model, X1 is salary, X2 is Y is salary, X is the number of years of experience. In multiple linear model, X1 is the salary, X2 is, let's say, education, X3 is, let's say, the industry, like that. Okay.
And what is Y
Not-
then? And what is
Yes.
Y then for the multiple?
Why is the salary? Why is still the salary, right? I am
And then
predicting
X1 is also the salary in this.
the first case Y is the salary, second case also Y is the salary.
Understood?
Output remains the same. In the
Correct.
first case, I am predicting Y based on only employees' age. In the second case, I am predicting salary based on not just employees' age, but other factors as well.
Okay, okay. You meant to say that X1 is like age, X2 will be the years of experience, X3 will be industry, and on and on.
Right, right.
I
right.
I misunderstood that X1 is also salary over here. So I said how it cannot be can be two.
No, no,
X
no,
and
no,
Y can be
no,
same.
no.
Okay.
Because why is the outcome? I'm
Understood.
I'm predicting salary. And if it is a polynomial, this means y equal to beta naught plus beta 1 x square. So this is simple polynomial model. Simple because it's still based on one input. Polynomial means that because it's not the degree is not one anymore. I am not saying that. So here I am saying that as your age increases, your salary is going to increase exponentially, not linearly. Okay. And multiple polynomial regression is beta naught plus beta 1 x1 plus beta 2 x1 square plus beta 3 x2 plus beta 3 x2 square, like that. Okay. So far, fine, everybody?
Yes.
Great. And you can see here the error. The error is the observed value. This is the once I have got this line. Okay. Or let us say that once I draw a particular line, I don't know whether that's the optimal or the best line or not. But whatever a line I draw, at any point of x, I will see two values of y. One value which is the actual observed value, and another value which is the value that this particular line is predicting. And the difference between this is the error. Our objective is to minimize this error. Okay. So can you think of a formula that I can write that will help to minimize the error? So I have to tell, so there has to be an objective function. I have to tell the model that look, you must try to achieve this. If you achieve this, then automatically this error will be minimized, and hence you have reached the point where the line that you have arrived at is the best possible line or the best fit line. So what is the model doing? The model is randomly putting lines like this, right? Randomly putting lines like this. and trying to
937.
move this way or this way. Okay. And my objective is to tell the model a rule that will help the model to figure out that will help the model to figure out that what is that line which will give me the optimum result. So can you think of that formula? What should be the formula that will help give the model the objective?
Calculate all the errors and square it.
Okay, so why not just add up the errors?
To remove this negative and positive
Right.
difference.
So many of you, some of you already know this basic thing. So the very basic idea is that you calculate this error and you add them up. But if you add them up, then there's a problem, because even if the line was something like this, which is clearly not the best fit line, if you probably add the errors up, the error will come 0. And the model will think that I have arrived. I have arrived means I have got the right line that is giving me the minimal error, which obviously is incorrect, because that is not the right line. Because this, if I draw this horizontal line, this means that y is not dependent on x at all. But mathematically it is true, because I have said that add up the errors. Hence, I cannot just add up the error. I should square the errors, because if I square the errors, then the negative values become positive, and then I should add up the error and then figure out that this value of error should be minimum. This particular method, is everybody okay so far? Yes or no?
Yes, yes.
Yes.
So time series will come later again. This particular method is called root mean square error. Okay, this is a popular formula which most of us have also studied probably in our high school, but that point of time probably we did not know the applications that much, but now we know the applications. So here you see y hat, yi hat. What is yi hat? Hat is the estimated value. So if I take this point as the x, okay, y hat will be this point. Okay. And yi will be this point, observed value. So y hat minus yi, okay, square of that. Now we don't just take the entire square, we actually, in order to find out the, normalize the value, we divide it by the number of points. So that, there can be two models. In one model, there are 20 observations, and another model, there are 30 observations. If I just take the simple addition of the sum of squares, then the model with the 30 observations is likely to score lower, because anyway, the number of points are more, the number of errors will be more. Okay, so that's why many times when we have to compare models, we need to normalize it by the number of points, number of observations. And then obviously, since it's a square, we need to bring it back in the same value, same range, by making a square root of it. Okay, just like standard deviation. It's the same thing that we do for standard deviation, so that there's a difference between variance and standard deviation, so that the difference in the number of points is neutralized. Okay, so square root of this is root mean square error. Okay, so far fine. Everybody?
Yes.
Now, in most of the regression problems, you actually do not measure RMSE, you measure another very important metric, which is called R squared. Okay. R squared is a very, very important metric in regression. The formal definition is R squared equal to, you can see, 1 minus unexplained variation divided by total variation. Now understand this carefully. What is unexplained variation? Now go to this formula. Yi minus yi hat square. What is yi? This value. And what is yi hat square? This value. This is an unexplained variation versus total variation. What is total variation? Total variation is yi minus y bar. Y bar is the average value of y. Now this difference between actual value and the average value is the total variation. So this much clear? This much clear? Yes or no?
Sir, once again.
Yeah. You can look at this picture. I have here a dotted line. So there is an additional dotted line here, this line. This line is the average value of y. On an average, what is the salary for all employees? That's the average. And then you have this line, regression line, or the best fit line, which is giving me the value of the salary against the age. Okay. And then there is this blue dots, which gives me the actual salary of different people. So I'm trying to measure two values. One value is how much is the actual salary of one specific employee different from the average salary. That is the denominator. So this difference is the variation for that particular individual observation. It's the total variance. So if I say if I have 100 employees and if the average salary is something and a particular employee's salary is higher than the average by a certain amount, that is the total variance that particular employee has over the average salary of that population. Correct? Yes or no? Everybody fine? Yes. Yeah. All good? Yes or no?
No, sir.
Okay. So there is, so this is the average salary of the total population. This is person A. The average salary is 100. Person A is getting 200. So what is the variation of person A from the average salary? 100. Correct? Is the total variation?
Yeah.
Okay. Now, what we are saying, the salary is dependent on experience. And we are drawing a line that indicates the difference of salary due to experience. And if I draw this line, which is the best fit line, this says the salary should be 150. If I consider experience, the salary of this employee should be 150, but the employee has a salary of 200. Is this clear?
Clear, sir.
Okay. That means the best fit line, which indicates the variation of salary based on experience, could explain a difference of 50 from the average salary. An average employee should get 100, but this employee getting 150, this difference of 50 is because of the extra experience of the salary of the employee. So that means this is an explained variation. The best fit line could explain the variation. Correct? Yes or no?
Yes, sir.
Okay. And the remaining 50, but actually the salary is 200, not 150. So where is the remaining 50 variation coming from? Why is the employee getting 50 rupees more than 150 rupees? That 50 rupees is unexplained by the regression line. The regression line is not able to explain why this employee is getting extra 50.
Understood, sir. Thank you.
So what will be my objective? To build a model such that what should be my objective? I should build a model such that
Unexplained shall be very less.
unexplained variation should be ideally 0.
0.
I should be able to explain all the reasons why I'm giving somebody 200 rupees as opposed to an average 100 rupees. Okay. So what is the ideal value of R square? If I have to measure a model's performance based on R square,
1.
1.
1. Right. So I now
Just for
can,
clarification,
yes, please.
so SSC is the unexplained variable
Yes.
and
That's the residual.
SSR is the explained variable or variation.
SSE, yes, this is the residual variation. This is, yeah, unexplained. Yes.
SSC is the unexplained variation and SSR is the explained variation.
Right. And this is the total. The total variation is.
So,
Yes.
so Professor, actually we learn in last semester in statistics. So this
Yeah.
R square coefficient of regression to
Yes.
check whether this model is fit or not.
Yes.
So if it is value nearby 1, it is best fit model. So we learn all these things in that statistics.
Okay. Okay. Very good. Very good. Okay, yeah, this is, as I said, this is a part of, and sometimes also taught as a part of statistics as well. It's not
Yeah.
no,
Whether
necessarily.
that model is fit or not. So we used to calculate error and this regression value R square. So
Right.
if it is more than 0.8, 0.9, it is best fit model.
Yeah, yeah. So yes, absolutely right. So why not 1?
So it is not possible. So always.
No, it's possible. Let's say I have a data point like that. When, so do not give any constraint of linear or something. When do you think R square will be 1? How can I draw a graph such that R square will be 1?
All
variation.
value on the base fit line. If all value on base
So
fit
when will
line,
that
then
happen? So no, I can't control the values, right? I can only control the best fit line. Okay, I cannot say that make all the values come to the best fit line because the actual values are actual values, right? I cannot change the blue lines, blue dots. How can I draw the best fit line such that the blue dots will remain where they are because blue dots are the real observations. Okay, I cannot change them. How can I draw a best fit line such that the R without changing the blue dots? How will the best fit line look like to get an R square equal to 1?
So if we have to join all the blue dots, then it will be like a wave,
Like
no?
this. Yes, I can make this, right? This line also has an equation. It's maybe a very high degree of polynomial equation. And if I tell the model that your job is to get R square equal to 1, do not worry about polynomiality. The model is going to find out this line. However high the polynomiality may be, the model is going to, that's the idea of running the model on a computer. Right? Because the computer humans will not be able to iterate so many times. Computers will iterate millions of times and finally arrive at this line, which will pass through all these points, where the R square will be equal to 1. Okay, but should we go for this line?
But this may not give the correct prediction.
Why?
Because if we try to build the regression and join all the dots, that will not be able
Yes.
to give the correct prediction for the future. No?
Yeah, but why? Go back to our example of these two students. One student which has studied all the 10 years question papers, another student who has studied the fundamentals. So, if we compare the analogy, which is student A and which is which two models? We have this model, the gray line model, and we have the red line model. Which is student A, which is student B? Student
Red
A
line
is
is
this. Red, yes.
Yeah.
Red line is student A. What is that? Gray line is student B. Because student A has studied all the question papers thoroughly. So here also this line has studied all the points very thoroughly and made sure that it goes through all of these points. Whereas line B has not studied all the points very thoroughly, but it has found out an overall trend, the basic fundamental behind how these points are operated. And as a result, if the next point, what is our objective? Our objective is to predict the next point, right? Now, if the next point happens to be somewhere here, which is following the trend, there is no deviation, there is no, no change of pattern, then A's prediction will be better than B's prediction. Model A will predict better than model B, correct? Yes or no?
Yes.
However, if the next point lies somewhere here, is not exactly following the pattern, then B's prediction will be better than A's prediction. So now the question paper pattern has been broken and a new type of question has come in without breaking the basic syllabus. It is there in the syllabus. So it is following the overall trend of all the points, but it is not following exactly the immediate trend. So now B's prediction becomes better. Now we have to balance between this is called the bias variance trade-off. So I need to ensure that I am not too much on B's side. In that case, I'll be too far away from the points which are likely to follow the pattern. At the same time, I am not too much towards A's side, in which case I am going to miss the overall pattern. A model will have a very high variance but low bias, whereas B will have a very high bias but low variance. Okay. So these are other connotation also, the way we select the training and testing data sets. So we spend some time on this. But this is the fundamental reason why I should not go for R squared equal to 1. The moment I tell the model that go for R squared equal to 1, it is going to find out an exact fit. So usually there will be a cutoff. R squared equal to 0.9, 0.95, etc. Now, what would be the cutoff? That is again where the business value comes in, because there you have to measure the cost of error from a business perspective. If you predict the salary, so let's say take the example of salary. Okay, so where are you going to use the model? You are going to use the model, let's say, to determine the salary of a new employee joining your organization. So you have to figure out that if this salary calculation is wrong, prediction is wrong, to what extent, if it's wrong, you can absorb it. To what extent, if you make it wrong, it will cause a major issue with your either the budget of your company, or it may have an impact on attrition. So those are the aspects where you find out the exact business impact of this error. Like you said, if you calculate R square equal to 8, R square equal to 9, but how do you know whether it's 8 or whether it's 9? That's where the business comes in. Okay. Statistics comes in where you are just calculating. If you're just calculating with a formula, there's no application in business, because the business will say that, okay, you are giving me a 0.8, 0.9, how, what does it mean to me? Why 0.8? Why not 0.6? So as a business, I should be able to calculate, should it be 0.8? Should it be 0.9? Should it be 0.6? And then tell the statistician, or rather the data scientist, that build me a model such that the R square is 0.8. That value of 0.8 has to come from business. Make sense?
Yes.
Now, some, little bit theoretical question, but just to clarify the concept, can the value of R square be greater than 1?
No, sir.
No.
No. What will make? Okay. Anybody thinks otherwise? What will make R square greater than 1? When the sum of residual is greater than the sum of total. Correct. Sum of total, if sum of residual is greater than sum of total, that means SS RES divided by SS total will be greater than 1. So in that case, minus, it will be, sum of residual by sum of total is negative, not greater than 1. Okay. So actually two questions. One is, can R square be negative? And the other is, can R square be greater than 1? Okay. Both are possible. Both are possible. In one case, if R square is greater than 1, that means sum of residual has to be a negative value. Sum of residual
Since we
has
are
to be a
doing the
negative.
square, since we are
Yes.
doing the square, negative will not come, right?
Negative will not come, that is right.
So, sir, value will be always in positive, this
Positive.
residual and total. And residual will never be more than
that is
total.
right. So yeah, okay. So but it can be more than 1. It can be theoretically more than 1 if the sum of residual is higher than the sum of total.
But sir, sum of total is itself sum of unexplained variance and explained variance. So how can it be
Yes,
more than
so,
one?
Yeah, so think about it. When this line is this way, if I create a best fit line this way, in that case, the sum of residual will be higher than the sum of total. So here the sum of, so my point here is where is the this one I'll explain it because this is difficult to explain over here. Next class I'll show you. Okay, both of these are theoretically possible. Both of these are I have to draw a graph and explain. Okay, not there here. Both of them are theoretically possible. That you can have R square value more than one. Okay, and that's why sometimes it's a very common question that though practically it will never happen. Okay, if you create the model, but theoretically it's possible where the sum of residual is higher than the sum of total, and that's what makes the R square value. Now, in that case, what will happen? In that case, the R square value will become negative. Okay, so R square can have a negative value. Even though it's a square, it can have a negative value. I'll explain this next class. I don't have the diagram here, but theoretically it is possible to have it like that. Okay.
But that may not be the best fit line then.
No, obviously it will not be the best fit line. Obviously it will not be best. I'm saying theoretically you can get an R square value which is negative. Okay, obviously it will not be a best fit. Okay. But just for theoretical understanding, so because you may have a feeling that because it's R square, it can never get a negative value. That is not the case. R square can have a negative value. Okay. But I will show you because it requires a diagram to be drawn and I have to explain you in that format. So next class I'll do that. Okay. I don't have the chart right now. Okay. Last, before we close, just a quick list of popular. So we'll start with the regression, and in regression we saw that we have this linear and polynomial and simple and multiple. And similarly for classification, there are certain types of fundamental model. One is called logistic regression, which is actually a derivation from regression. Then there's something called a decision tree. Decision tree is nothing but an if-else kind of thing. Okay. Then there is a model called K nearest neighbor or KNN. Okay. Then there is a model called Naive Bayes. This is from Bayes theorem. If you have studied Bayes theorem in statistics, then this is derived from Bayes theorem. Okay. Another one is support vector machine. And the last one is a neural network. So neural networks actually get into the deep learning. So based on the neural network, you get into something called deep neural network, which is a part of deep learning. But we'll not get into deep learning in this course, but we will talk about these 6 models. Okay, broadly the 6 models. Okay. So far fine, everybody?
Yes.
Great. Okay, so I think we'll close here today. So next class, we are going to see the concept behind decision tree, and then we'll get into the hands-on. Okay. I hope everybody has already installed 9. So we'll start with 9, but then we will get into also Python, because these days coding in Python is also very easy using JVM. Okay. Any other questions before we close for today? Great. So thank you very much. I'll see you then the next Saturday.
Thank you, sir.
Okay. Okay. Bye. Bye, everybody. Bye.
Thank you.
Thank you, sir. Thank you, sir. Thank you.